Algebra 2, Lesson 30, Part A, is called Deductive Reasoning, and that's actually what goes in our first blank. Deductive reasoning is the process of reasoning from a major premise, which is a non-reversible statement. We'll get to this stuff, to these terms. So reasoning from this statement to arrive at a conclusion. The major premise is a conditional statement, which means it can be written as an if-then. So we'll get into that. Let's just fill this blank in. Deductive reasoning. Okay, and like it says, the major premise is conditional. So we can write it as an if-then. So let's look at the statement. Julie wears goggles when she is swimming. That means if Julie is swimming, then she's wearing goggles. So that's down here. If A, then B. That's what this is indicating, a shorthand for that. If A, then B. Our A is Julie is swimming. That's called the hypothesis, the if part. And the then part is the conclusion. If this happens, then we can conclude that that happens. All right? Every major premise can be written as an if-then. Sometimes they'll start out that way. Sometimes you need to rewrite them. All right. So, next term we have here is syllogism. Another word for that could be an argument. I'm going to put /argument. Okay, that is a 3-step deductive reasoning process. And it's got these 3 parts. We have a major premise, which is that one that can be written as an if-then. And then a minor premise. And then we reach our conclusion. So we're going to label a few things here. First we'll mention this is a 3-step deductive reasoning process. Okay, a 3-step deductive reasoning process with 3 parts. Well, yeah, these 3 parts. Major premise, okay, and this can be written as an if-then. It's a conditional statement that was mentioned up above, so can be written as if-then, an if-then statement. The minor premise, if we have a valid syllogism, identifies someone or something as belonging to the group named in the if part, in the hypothesis. So this identifies someone or thing as belonging to the group named in the hypothesis, to group named in the if part of the major premise. Kind of a lot to write in there. And then the conclusion states what was named in the minor premise has the characteristics described in the then part. Okay, we reach the conclusion. States that what, or sometimes it's who, but that what is named in the minor premise has the characteristics stated in the then part. Conclusion of the major premise. Okay, so that's a good generalization explaining what happens. And let's look at some examples. It'll make more sense when you see the examples, I think. Okay, so here's Julie with her goggles again. If Julie is swimming, then she wears goggles. That's our major premise written as an if-then. minor premise is Julie is swimming. So this identifies someone, in this case, as belonging to, going along with this if part. If Julie is swimming, she's swimming, okay, then she wears goggles. So we can conclude the then part. If the minor premise matches the if part, then the conclusion matches the then part. If the minor premise doesn't match the if part, we cannot reach any conclusion at all, because we're not given any other statements. It's just this one if-then statement. But this is a valid argument or a valid syllogism because the minor premise matches the if part of the major premise. All right? I'm just going to write valid beside there. You can write other notes to yourself. I'm going to go ahead and look at this other example. There will be a quiz every Wednesday. All right, that is not an if-then statement, but we can rewrite it as one. So, if it's Wednesday, then there's a quiz. I'm just going to write then quiz. Okay, if Wednesday, then quiz. It's Tuesday. That's the minor premise. Okay, the minor premise says this particular day is a Tuesday. We look at if. This says if it's a Wednesday. These don't match. We cannot reach any conclusion. We know that every Wednesday there's a quiz. We don't know what's happening on Tuesday. It might be a pop quiz. So we don't know there's not a quiz. This is invalid because that minor premise doesn't match the if. Okay, now, sometimes you might start with a statement that you know is not true. But we can still talk about whether the argument is logical. Okay, so that's what we're getting to down here. Please note, it doesn't matter for the purposes of the logic whether one or both of the premises are false, major or minor. There still can be logic followed. It's like, if this were true, then that would be the case. We know that not all chickens have 3 legs, but that's our major premise in this next example. So, and then it says Penny is a chicken. Okay, so we're going to rewrite the major premise as an if-then. So if an animal is a chicken, then it has 3 legs. I'm just going to abbreviate that. So if chicken, then 3 legs. Okay. Minor premise says Penny is a chicken. Something being a chicken matches the if part. So we can conclude the then part. Penny has 3 legs. Okay, this is valid, even though we know that major premise isn't actually true in real life. Okay, and about this time, someone would try to tell me, this isn't math. It actually is. This is going to lead into proofs later. You need to be very logical. You follow a logical process in everything you do in math, but definitely when we're doing proofs. Also, the good life skill, because people sometimes try to seem like they're being logical and reach the conclusion they want to reach in order to influence people. And so it's good to be aware of that and be able to reason through these. So it's good practice for that also. All right, moving on. Whoops, wrong page. Part B is about Euclid. Okay. First, actually, we're starting with some definitions. Then we're going to get to this list of 10 postulates that Euclid had come up with, which will be very useful in our reasoning processes. So, names given to ideas or things. That would be definitions. Okay. And all definitions are reversible. Lines are parallel, and that's not a typo. That is read if and only if, that IFF. Okay? When we're reading this aloud, or even in your head, think if and only if. If and only if. They are in the same plane and do not intersect. That means if you're told lines are parallel, you know they're in the same plane and do not intersect. But also, if you know two lines are in the same plane and do not intersect, then those lines are parallel. So it being reversible means it doesn't matter which side of the if and only if you know, you can then conclude the other part. Okay. Now, there are a couple of different kinds of assumptions, and they each have their own name. An assumption that is true everywhere, in all areas of mathematics, that is called an axiom. And an assumption that applies to a particular branch of mathematics is a postulate. Either way, those are assumptions. They are things that we just generally take to be true without proof. Okay. A statement that we can prove by using definitions, postulates, and axioms in a deductive reasoning process, that is a theorem, not a theory. A theorem can be proven. Okay. And this is used a lot when we're proving things, the reflexive axiom. Is a formal recognition of the fact that everything is equal to itself. Okay? Now, here are 10 postulates that Euclid came up with. Actually, he had whole books of things, but these are 10 that are very, very useful. A lot of them you're going to think are just duh statements, because again, they're postulates. They're assumptions we make. We just know that they're true. 2 points determine a unique straight line. If you have 2 points graphed and you draw a line through it, like there's only one line you're drawing through those 2 points. Postulate 2, a straight line extends indefinitely far in either direction. Right. Postulate 3, a circle can be drawn with a given center, any given center, and any given radius. You put a point somewhere, you can draw a circle around it, as big as you want. Postulate 4, all right angles are equal. Of course, because each one of them measures 90 degrees. Okay? Again, postulates, things that we just assume to be true. We don't have to prove them, we just know they're true. So this one, given a line and a point that is not on that line, there is somewhere in the plane that they're on a line that goes through point P that doesn't intersect with N. There's some parallel line to N that goes through that point. And just one. Postulate 6. Things equal to the same thing are equal to each other. 3 plus 1 equals 4, 2 plus 2 equals 4, therefore 3 plus 1 equals 2 plus 2. Okay, same kind of thing here. If equals are added to equals, the sums are equal. Postulate 8 is about subtracting from equals. They're going to be equal too. Figures that can be made to coincide are equal. It's talking about congruent shapes. Like you have 2 triangles, and if you can turn one or flip it or whatever you need to do to make it totally match up with the other one, then those triangles are congruent. And postulate 10, the whole is greater than any part. The whole thing is bigger than a piece of that thing. Okay, so these are the postulates. We'll be using some of those more than others, but you have them here to refer to. Okay? And then we move on to part C, which is about vertical angles. And there's some things that we were assuming to be true, but now we're going to be able to prove them. Okay, and actually that's called, we postulate something if we're just accepting it, even though it can be proven. So it's more of a theorem. All right, so look at the diagram we have over here, this drawing. We know that x plus y equals 180 degrees because these two angles together form a straight angle. So we know x plus y equals 180. Okay? But we also know, here's another straight angle, we know that x plus z equals 180. And then, let's take a look at Euclid's postulates. Like maybe number 8. If equals be subtracted from equals, the remainders are equal. Okay, so x plus z is equal to that. Or we could also, instead, let's just do this. Let's use postulate 6 instead. Things equal to the same thing are equal to each other. Each of these is equal to 180. Okay, x plus y equals 180, x plus z equals 180. This is a little bit more direct, I think. Postulate 6 would tell us x plus y equals x plus z. You kind of already know that. We use that when doing substitution method to solve systems of equations. So you have that, and now we're going to use 8 because we're going to subtract equals from things that are equal. Okay, so this is, actually postulate 8, and we're subtracting equals from equals, and we're getting that y equals z. We have just proven that those vertical angles are congruent. And you could do the same thing to prove, the same process, to prove that x and p are equal as well. There, we just proved that vertical angles are congruent. Okay. Then we're moving on to part D. And part D is, you hopefully already, you remember these, I hope, because you've seen this before. Corresponding angles, alternate interior angles, and alternate exterior angles. They're congruent to each other. So interior means they're in between the parallel lines. We have two parallel lines crossed by a transversal. Interior angles are between the parallel lines. Exterior angles are on the exterior. They're on the outside, not between. And then corresponding angles are in the same relative position. Okay, here's one of the parallel lines to the left of the transversal and above the parallel is A. To the left of this transversal, above this parallel line, A. Okay, they're in the same relative position. They're congruent to each other. Basically, whenever this happens, all the angles that are acute are congruent to each other, and all the angles that are obtuse are congruent to each other. And the book mentions, if you happen to want to read that, Euclid used his postulates to make this it was a pretty long proof that is above the level of math that we're in right now. But it can be proven. This is one of those things we're postulating because it can be proven, but we aren't ready to prove it yet. So we accept it to be true. Okay, so part D is just reminding you about that. And then we're going to go ahead and look at part E. It's going to be related to this because we're going to use some of that for this part. 180 degrees in a triangle. You have known this for a long time. You just accepted it. Probably. But we can prove it. Okay, so what we're going to do, I didn't bring a straight edge with me, but here, if we extend that, so here's a line, right? And then we could draw a line parallel to that right through there. That would be, which postulate was that? That's postulate 5. Okay, postulate 5 tells us here's a line, The vertex up here at the top, that is a point in the same plane, not on that line. There is a parallel line to this one that we can draw through that point. So that's supposed to be it right there. Okay, so this is parallel to that. And now we have two parallel lines crossed by a transversal and alternate interior angles. They're on alternating sides of the transversal, interior between the parallels. Okay, they're congruent. So those two are the same. That means this is A. But same two parallel lines. Here is another transversal right there. Alternate interiors here are the same. This is C. Okay, because, let's label that a little bit. These are alternate interior angles, so they're congruent. And also those two that are labeled C now, those are alternate interior angles, so they're congruent. If this is C, this is C. These three make a straight angle. They add up to 180. Okay, A plus B plus C equals 180. But A plus B plus C were the interior angles in that triangle. We have just proven that all three angles in any triangle add up to 180 degrees. And that concludes the notes for lesson 30.